In this video, we will talk about test standardization. In particular, we will talk about rescaling of standard scores to easily understood numbers and norming or standardization samples on which measurements are used to derive the conversion. And these are essential elements of every assessment test. As you recall from our presentation of standard scores, when we have a set of measurements on a test, we can subtract the mean and get to a standard set of measurements with a mean of 0 and the same standard deviation as the original. And then by dividing with the standard deviation, we get to standard scores which have a mean of 0 and a standard deviation of 1. And these are the z-scores, and they are essentially the original scores expressed as number of standard deviations away from the mean. Now, these kinds of numbers are not very easy to perceive or remember for many people because they have decimal digits and they're also often negative, indicating performance below the mean. So negatives and decimals make these numbers a bit cumbersome for many people. And therefore, what we can do to correct that and make them more convenient without changing their essence is to transform them to any distribution we like. So if we multiply by a number such as 15 and then add 100 to every one of them, then we can derive exactly the same distribution again, and of course the same as the original raw scores, but this distribution has a mean of 100 and a standard deviation of 15, the two numbers that we used to derive it. So someone who was 1 standard deviation above the mean is now 15 above the mean because we multiplied everything by 15. Someone who was 2 standard deviations below the mean is now 2 times 15, that's 30 below the mean. 30 below 100 is 70. Someone who had exactly average performance would be at 100. So what we did was to transform our actual distribution of raw score that we measured into an identical distribution with a mean of 100 and standard deviation of 15, which are numbers that are easy to remember when we know and do not forget what they represent. So standardized scores can be scaled. The original standard score is the z-score, but we can scale them to be like an IQ scale, and these are with a mean of 100 and standard deviation of 15. This is what IQ scores actually are. They are standardized numbers that are made to have a mean of 100 and a standard deviation of 15 based on the actual raw scores of how many questions were answered, which are uninformative numbers in themselves, because in order to interpret those properly, we would need to know the mean and standard deviation of everyone answering the questions on the test. There are other scales that you are probably familiar with, such as whisk subscales, which are made to have a mean of 10 and a standard deviation of 3 using an operation similar to the one we just demonstrated. And there are many other possibilities of scaled scores that are used in assessment tests, and they all have the same interpretation. You remember, always think of percentiles. So all kinds of scaled scores are informative to the extent you know what percentiles, what proportion of the population each score corresponds to. Standardization of a test begins with selecting a sample, that is, a group of people, adults or children, to be measured. This is called the norming sample, and it is extremely important for the norming sample to be representative of the population. That is, to have the same mean and standard deviation as the whole population. Of course, we can never measure everyone, so we have to carefully select our sample so that we can reasonably expect it to have a mean and standard deviation that will be very close to the whole population. So they must have the same average performance and a similar dispersion of performance as over the whole population. Once the norming sample is selected, everyone in this sample is administered the test, and the distribution of scores on the test is checked to make sure it conforms to the normal distribution or is brought to conform to it. And after that, we can calculate a mean and standard deviation, expecting that to express the population, and then calculate z-scores and provide conversion tables to z-scores, other standardized scores, scaled scores, and eventually percentiles. So for each raw score, we can express the corresponding z-score or scaled score or percentile that it corresponds to. And these are the tables that you see accompany every assessment test, where you look up your raw score and derive a scaled score or a percentile or both. So the result of the test is a percentile rank, the proportion of people in the norming sample. This person performs better or worse than. So a relative standing. And this percentile is generalizable to the population to the extent the norming sample was representative. Remember, percentiles derived from a test are actually corresponding to rankings with respect to the norming sample from which the conversion tables were derived. Now let us look at some examples of interpreting such scores. Let's start with the case of full-scale IQ, which is scaled to a mean of 100 and a standard deviation of 15. So what does a score of 100 on an IQ test mean? Well, 100 is equal to the standardization mean. By definition, we make IQ scaled scores to have a mean of 100. So this is a z-score of 0, not away from the mean, exactly equal to the mean. Therefore, it corresponds to the 50th percentile. This means half the people score better and half score worse or equal to this score. So an IQ of 100 means you are in the middle. What does an IQ of 130 mean? Well, 130 is 30 above 100, 30 above the mean, and 30 is twice the standard deviation of 15. So an IQ of 130 means 2 standard deviations above the mean. That is a z-score of +2, which corresponds to the 98th percentile. Note that we don't usually use decimal places for percentiles. We round them up to integers so that they're easier to interpret. So we say the 98th percentile here. What about an IQ of 80? Well, 80 is 20 points below the mean of 100, and 20 divided by 15 means that's 1 and 1/3, 1 and 1/3 standard deviations below the mean. This is what 80 means. 80 means a z-score of -1.33, which corresponds to the 9th percentile. So someone with an IQ of 80 has a score that is expected to be lower than 91% of the population and equal or better than 9% of the population. And this is the meaning of an IQ equal to 80. Let's look at a different scaling, turning to which subscale type scaling, which are standardized to have a mean of 10 and standard deviation of 3. What does a subscale score of 10 mean? Well, that is equal to the standardization mean. That is a z-score of 0 corresponding to the 50th percentile. So a scale score of 10 means that you're doing better than half and worse than half the sample. You are in the middle. What about a subscale score of 13? Well, a 13 is 3 above the mean, which is 10. So that is one standard deviation above the mean. A z-score of +1, one standard deviation above the mean, corresponds to the 84th percentile. So a standard score of 13 means that you are doing better or as well as 84% of the relevant population. So children of your age, if you're talking about the WISC. What about a scaled score of 8 on a WISC subscale? Well, 8 is 2 below the mean of 10, and that is actually 2/3 of a standard deviation, 2/3 of 3. So 2/3 of a standard deviation below the mean is z equal to minus 0.67, that's 2/3, which corresponds to the 25th percentile. So a scale score of 8 means you are doing worse than 75% of the norming sample, and as well or better than 25% of that. What about a scaled score of 4? 4 is 6 below the mean of 10, and 6 is twice 3, so 2 standard deviations below the mean. This means a z-score of -2, which corresponds to the 2nd percentile. So a scaled score of 4 means you're doing worse than 98% of the norming sample or of the corresponding comparison population. We must be very careful with interpretation of test scores. And remember that although they look like numbers, they're very easy to misinterpret because they don't mean what actual numbers mean. What I mean to say with that is that scaled scores are not on a ratio or interval scale. First of all, distances aren't comparable. So the difference between two people who have 115 and 105 scaled scores of IQ or intelligence quotients, and the difference between two people who have 80 and 70 is not comparable. They both look like 10-point differences. They are 10-point differences, but that doesn't mean they're equal differences. There is nothing that can be said about comparing these differences because these numbers aren't on a scale that has distances. And much more obviously, ratios are completely meaningless because there is no zero on this scale. So there is no sense in which you can say that an IQ of 120 is 50% higher than an IQ of 80, or that an IQ of 150 is 100% higher than an IQ of 75%, or double that, or anything of that sort. These are completely nonsense statements. The only valid interpretation of test scores is as percentiles. And that's why you always need to have a conversion table handy so that you can convert the scaled scores to z-scores or directly to percentiles and know what your performance, your test performance means in terms of proportion of the population that does better or worse.